Hello, everyone, and welcome back to Psychology 301, Chapter 3 on Variability. I am Jill Yamashita, and I will be leading this talk on Chapter 3, Variability. The quote for this chapter is by Aquinas, who said, "A small error at the beginning can lead to great ones at the end." And this is especially true with math because a problem that has an error at the beginning of working on the problem carries throughout the whole problem. The learning outcomes for this chapter is to 1, define variability, variance, standard deviation, and standard error of the mean. 2, calculate the variance, standard deviation, and standard error of the mean. So let's begin. Variability is defined as a number that provides an index measuring dispersion or how spread out scores are. The more spread out scores are, the larger the variability, and the less spread out scores are, the smaller the variability. An example of variability is the range, which is the highest score minus the lowest score. So that shows you the range of all of your data. Index and variability that we're going to deal with today deals with 3 different things. So first of all, index of variability is the tendency of scores in a distribution to be widely spread or dispersed about a given central point. Usually that central point is the mean. So we already went over the range. The ones that we're going to be focusing on right now are the variance, standard deviation, and standard error of the mean. And that's exactly what the overview is for Chapter 3. Now it says sample variance, sample standard deviation, standard error. Sample just means that we took a part of the population, a sample of the population, and used that to determine our variability index. So let's start with the sample variance indicated by S squared. Sample variance is using the mean as a reference point, the average of the squared differences. Now, squared difference is basically a deviation squared. A deviation is the difference between the score and the mean. So yi minus y bar. Here is the definitional equation for our sample variance. We have S squared. Now S squared is our sample variance, so that actually indicates sample variance equals, again, this is our uppercase sigma. This means the sum of. And here we have a deviation, yi minus y bar. So you take the deviation, but we're going to square it. Because if you just took the sum of the deviations, it would always add up to 0. And having a variance of 0 doesn't tell us anything. So we must square each of the deviations and then add it. Take all of that and divide by n minus 1. Now this isn't divided by n, which is a number of scores in the group. It's divided by n minus 1 because this is now based on a sample. And whenever we use a sample, we need to be extra conservative or careful, so we use n minus 1 on the bottom. Now this is defined as a definitional equation because exactly what the variance is. It's the sum of the deviation squared divided by the number of scores minus 1. But what we're going to use is the alternate equation. Sorry about that. The alternate equation for S squared uses something completely different. Here is the equation. Now it might look scary. It's called computational equation because it actually is easier to use. So here we have the first part of the equation, the sum of y squared. Now the sum of y squared simply means we take each value or each score in our data set and we square it. And then we add up all those squared numbers together. So that's how we get this first number, the sum of our y-squares. The second part of the equation on the top, well, we're going to subtract out the sum of y squared divided by n, the number of scores. So on the top we have the sum of y, so that simply is the sum of all of our data added together. So we take each score, we add them to all the other score values, and then we take that value and then we square it. We take that squared number and then divide by n. And that will give us the top part, which is also known as the sum of squares. That is then divided by, again, n minus 1. And we use n minus 1 because it is, again, based on a sample. Okay, so this is also known as the sum of squares for the top value and degrees of freedom for the bottom value. But we're not going to worry about labeling things right now because that will just complicate things. But if you definitely have questions, don't hesitate to ask in the class period we have set aside for chapter 3. Okay, so we're going to take a data set and we're going to solve. So the first thing I need to do is I need to take the values in this data set and we're going to take each one and then we're going to square them. So we have 5, 8, 7, 6, 6, 4. So we have 5 squared plus 8 squared plus 7 squared plus 6 squared plus 6 squared plus 4 squared. And that will give us our first value. From that, we're going to subtract out. Now again, it's the sum of y, sum of our values added together. So just like you would, 5 plus 8 plus 7 plus 6 plus 6 plus 4. We're going to take that value and then square the sum. And then take that, divide by 6, because we have a total of 6 values. Okay, that's the top number, and that's all divided by n minus 1, which is 6 minus 1, or 5. Okay, so 5 squared plus 8 squared plus 7 squared plus 6 squared plus 6 squared plus 4 squared gives us 226. Minus, well, 5 plus 8 plus 7 plus 6 plus 6 plus 4 is 36. We want to square 36 and we get 1296. Divide by 6 and we get 216. So on the top we end up with 226, which is the sum of our y squared, minus 216, which is the sum of y. Take that value, square it, divide by n. And then after you subtract the top, so 226 minus 216 is 10. Then you divide it by 5, and that gives us a variance of 2. And that's how we solve for the computational equation. So for this one, I want you to try to do this. I want you to pause the problem and then solve for it. All right, so the next thing I'm going to talk about is the standard deviation. But the question I oftentimes get is, why do we need to solve for the standard deviation when we have the variance? And that's a very logical question. I mean, we have the variance. Why bother solving for the standard deviation? Well, the thing about the variance is that in order to solve for it, we need to take the deviation and then square it. Well, when we square a number, we don't just square that number, we also square the units that it's measured in. So when you solve for the variance, if you measured it in inches, you'd have inches squared. That doesn't really work for us when we report our descriptive statistics because our mean, which is in inches, doesn't work with variance, which is in inches squared. So by converting the variance into the standard deviation, we then convert our squared units into our standard units again. How do we do that? Well, we actually solve for the square root of the variance. And that's how we get the standard deviation. It's that simple. So we take the positive square root of the variance, and that allows us to solve for the standard deviation. So again, the reason why we need to solve for it is that we need to get back to the units we measured our data in. So when we solve for the standard deviation, again, it's simply just the square root of the variance. Now, this is an example of what's called a normal distribution curve. It shows the whole entire population. And when we talk about standard deviation, it actually is a specific unit that is used in math. So if we have between -1 and +1 standard deviations, that includes 68% of the population in that curve. If we go from negative 1.96 standard deviations to a positive 1.96 standard deviations, that gives us 95% of the population. So standard deviations gives us not only the standard units, but also gives us very specific pieces of information about the variability of our data. Okay, so standard error, or SE, is also known as the standard error of the mean. Now, this is a new index that basically estimates the standard deviation instead of for a sample for the population. So it estimates the standard deviation for a population. The equation for the standard error of the mean is equal to S, again, S is standard deviation, divided by the square root of n. N is the number of scores we have in our data set. Okay. So let's say that we have a variance equal to 12.8. We solve for the standard deviation. We take the square root of 12.8 and we get 3.58. For a standard error, let's say that we have 6 people in our data set. We know the standard deviation is 3.58. We're going to put that into the equation. So we have S, standard deviation of 3.58 on top, divided by the square root of 6. Again, n is equal to 6, or the number of scores we had in our data. So 3.58 divided by the square root of 6 is 1.46. And that's how we solve for the standard error of the mean and the standard deviation. If you have questions, please don't hesitate to ask in our synchronous class. Have a great day. Bye.